if I understand correctly, you are. Oh, it's gonna display. It's really gonna give me some trouble on my first day back. What? What? Oh, why is my screen suddenly blank? You're on example 5, correct? Oh, here we go. Example 5. Yes. Take a moment to discuss with your neighbor what you know about the graph of this function using everything that you've talked about so far.
The degree is 5 that's on. And then what's what A? Like there's things positive and the one. Oh, I kind of just negative. Yeah. Yeah. Okay, so negative.
Okay, you ready? It's been a while. So tell me, well, yeah. Can you please show me the end behavior of this graph? Okay, we know that it's opposite because the degree is odd, and we know that it's this way because of that negative leading coefficient. Now, how did Ms. Mosesian mention you should write the end behavior? Was there a particular format she was using? Or just pictures? Okay. So kind of in our mind we have this. It seems like this is what you have going on. Is that right in your mind? Okay, so how would you say this? I don't know the word she used. Rises to the left, falls to the right. Okay. I don't mind a little diagram. If this is a test or quiz, you could do just what I did. Picture's worth 1,000 words, right? And you can see here, right to the left, fall to the right. And I'm gonna leave it like that. List each zero and its multiplicity. Okay, I'd like to hear, Katie, do you know any of the zeros here? -1/2. Okay, and multiplicity. Do we agree? Multiplicity is 2. Thank you. And Joanna, any others? Multiplicity is 3. Cool. Determine whether the graph crosses or touches the x-axis at each intercept. So we know that when multiplicity is even, it touches it, and when it is odd, it crosses. Okay, so -1/2 is 0. It's a touch. And 3, 0, it's a cross. Multiplicity 3 is not just any cross, though. It's a cross with a twist. Did she talk about that at all? So I'm sure that you looked at the function y equals x cubed, didn't you? Did you look at that last time? So this will be just a cross, just like a line. So going through it. So a twist just means that there's a little bit of like a rising one way and then a falling the other way, like a squiggle or twist going on there. Okay, and use this information to draw the graph of f of x, noting the behavior of the graph at each of the x-intercepts. Did you already graph this? Did you graph it? Oh, yes. If it's 3, 5, 1 is the only odd one that doesn't twist. All the other ones twist. All the other odds twist. Good point. I'm gonna come around and just see what your graph is out. If your graph together, then take a moment to pull that together if you can. Okay, yeah.
Is it the twist in the multiplicity involved, or?
Or multiplicity is 3, there's right, so cross with a twist. Yeah. Oh, I guess I got the wrong number. Thank you. 50. And check with the people around you, not just your neighbors, maybe in front of you, behind you.
Oh, yeah.
Or the, we're kind of one.
Five, yeah, 5, 0. Yeah.
Okay, we ready? Right, you start with that, which you know. We know that the zeros, and you can't really start with that behavior, but on the graph, you know that the zeros are -1/2, comma 0, and 50, right? And now we can put in the end behavior. We know that it's going to go down like this, up here. Does that make sense? Is that kind of what you're doing? I'm going to adjust it a little bit as we go. At that -1/2, we know that it touches it, so it's going to just kind of do this kind of thing. It's got to be curved. I don't want to see a corner, or I don't want to see anything like, I don't want to see this. It's not a bounce. It's a nice smooth curve. So if we would have kept that in mind from the beginning, maybe we could have done something like this. And then I know that at the other one is going to not just cross through it, right? This would just be like a straight cross without a twist. So what I'm looking for is kind of like you're touching down with an airplane like this, and then I'm going to adjust this a little bit to look like this. So that's what the twist would look like. Any questions? Yes.
Would you repeat like when there is a twist?
Yeah, it's twist because this is odd greater than 1. I'll say odd 3 or more. So twist. So in other words, the only time it crosses through without a twist is when it's a multiplicity of 1. Every other time it will have a twist. If you hate that, if you want to reject it, it's a very small nuance that you'll be fine without it. I'd like to give you a complete understanding of what the graph looks like. Let's move on. I'll give you a moment to get a good graph going here. We're going to go right to the graph you made. Just like consider these things. Check with your neighbor when you are done or stuck. Ready to go over it? Ready or not? We're going to start with the zeros, which are at -2 and 1, yes. At 1, there is a multiplicity of 2, which means it's going to touch that x-intercept. And I'm going to combine that with the end behavior, which we know is the same as the last one, isn't it? So at that 1, I'm just going to start with that nice rounded thing going right there. And then at -2, we know it has a multiplicity of 1, so it's going to cross with no twist. So just like that. Does this match what yours is? And I believe so far we have ignored the y-intercept. Would it be difficult to get the y-intercept? Wouldn't be difficult, but just we're looking for behavior of the function right now. Eventually I will be asking for y-intercepts. Normally we don't really care about the y scale. So don't try to be overly accurate. A lot of students try to come like way down. We're not trying to look at that right now. It's just the behavior at the zeros, the end behavior, turning points. Talk about turning points. Did you mention this at all, turning points? Okay, turning points is exactly what it sounds like when it turns around and goes the other direction. It's called a turning point. So if you look at this graph, you can see that there are 3 of them, right? It's going down and then turns and goes up. That's a turning point. It's going up and turns and goes down. That's another turning point. So when it changes direction. So if a polynomial function is of degree n, then the graph has at most n minus 1 turning points. For example, quadratic function looks like, show me, quadratic function looks like this. How many turning points? Just 1. So it was degree 2 has 1 turning point. So that's a generalization for all polynomials. The most turning points it can have is n minus 1. So 5th degree could have up to 4 turning points. It could have fewer though. It could have fewer. Like, do you know what the graph of x to the 5th power looks like? Well, let's not do x to the 5th. X to the 4th. To the 4th. It's kind of like a parabola. X to the 4th just looks like a parabola with a flattened bottom. 1 turning point. But it could have more stuff in it if there's other coefficients like x to the 4th minus 3x cubed plus 2x. Oh, that's me. My bad. Okay, so which of the graphs below could be a graph of this guy? So go ahead and discuss what we talked about. Which one could be it?
I think it's like.
Don't forget Katie's behind you.
Degrees.
Actually, no. I guess, everything.
Yeah.
Yeah.
Okay, do you think it's the first, second, third, or fourth graph? Which one is most likely? Well, first, second, use your fingers from first, second, third, or fourth. So A, B, C, D. Okay, so take a look around and see what other people are thinking. Okay, would like to tell us what they think it is and why? Well, did you cross out C? First of all, you cross out C because It has 5 turning points. You know that if it's fourth degree, then the most it could have is 3. So there's not a whole lot of work to be done. You also probably crossed out D because they're both going up. The leading coefficient doesn't match the graph. Is that the kind of thought process you did? But then how do you know if it's A or B? Did you use a calculator? The y-intercept. We know the y-intercept has to be negative, so we had to cross this one out. Cool. Intermediate value theorem. When you refer to this guy, we call it IVT. You're short not to misspell it. I had to save a little bit of time when you're talking about IVT. I'm going to give you a picture of what the IVT normally does, intermediate value theorem does. It's always about an interval, a closed interval. And put your pencils down for now. I'll give you a chance to graph in just a minute. It's a closed interval, so I'm going to do this. And I'll say that this is f of a. In other words, I have this point here, and down here is f of b. So if I have these 2 points on a polynomial, f of a is greater than 1, f of b is, I said f of a is greater than 0, f of b is less than 0. What do you think is true that's going to happen on this interval or in this interval? Yes, Ellen. Does that make sense? There has to be a 0 between A and B? Exactly. 1 real 0? Or could there be more? There could be more. How many could there be? A million? There could be a million. Normally, an intermediate value theorem guarantees 1, the existence of 1. So, but what we say is there is at least 1 real 0 between A and B in this situation. So I'll go ahead and make a for instance graph. We're going to need a couple sentences here. So if f of x is a polynomial, and f of a is greater than 0, and f of b is less than 0, IVT guarantees that there is at least one value c in this interval such that f of c equals 0. As you can tell from last time and this time, zeros are kind of a big deal with polynomials. Sometimes you can find them quite easily. Sometimes you won't be able to find them unless you have a calculator. Right? Does it have to be f of a is greater than 0 and f of b is less than 0? No, it just has to be opposite. So this is just in this particular case. Does the idea make sense? So don't worry about exactly how I wrote it. I don't want you to memorize anything. I'm going to be able to picture what's going on. This is less than this is greater than this. Something in between, if there must be a 0, and say it appropriately. So for this one, show that the polynomial function that has a real 0 between 2 and 3. How are we going to do this? We want to use the intermediate value theorem. When it's asking you to show that there is a 0 and it gives you an interval, use the intermediate value theorem. So first order of business is to find. Well, I'll give you a moment. What do you do first? So you plugged in 2, or plan to plug in 2, and plan to plug in 3. Is that what you were thinking? Is that difficult to plug in? No. Go for it. Is that -1? I could do this work, but I hope it makes sense that if these numbers are just gnarly, you could just tell that if I have like 27.3 and a 6.8 and a 5.1, it doesn't matter exactly what it is. What matters is that it's greater than 0, because this one was less than 0. So that's what you have to focus on. Is it greater? Is it less? Now this one was pretty easy to calculate. This one isn't too bad. Let's see, 27 minus 11. It's not too bad. But if the numbers are gnarly, don't feel like you need to grab a calculator somewhere. You can get the general idea of if positive or negative behavior. Okay, so show that this polynomial has a 0 between 2 and 3. Have we finished? We finished conceptually, but we have to say the words. Since f of x is a polynomial, I'll say in this case with. I felt like there are too many ands last time. With f of 2 less than 0 and f of 3 greater than 0. The IVT guarantees that there is a 0 or there's a value c in the interval 2 to 3 such that f of c equals 0. That sums it up. Any questions? Oh, did you finish before 8:30? Look at that. We are going to start the quiz at 8:30. After that, I need you to open up your laptops and do the student survey.